So we're going to look at how you find inverses of equations of functions today instead of just ordered pairs. So to start with, since an inverse switches your input and your output values, we're going to swap our x and y variables, and then we're going to solve it for y. So if you switch x and y's locations, don't change anything else, and then solve to get y by itself, so subtract 1/2. Divide both sides by -3, which it's actually easier to multiply by -1/3 since there's a fraction involved on the left-hand side of your equation. Then you're going to have to multiply everything by that -1/3, which gives you -1/3 x plus 1/6 equals y. So that's the equation of your inverse relation. If you look at B, same idea, it has function notation. I'm just going to change that to y equals, and then, like I did before, switch the location of what represents my input and my output variables. And then to undo the fact that we are multiplying by 1/27th, we're going to divide by 1/27th, which is the same thing as multiplying by 27 over 1. And then that's y to the third, so we need to take the cube root. If you do the cube root of both sides, you're going to have to break down that 27 that's inside there, but the cube root of 27 is just 3, so you get y equals 3 times the third root of x. Okay, so not every single function is going to have an inverse that's a function. The inequality tacked on here kind of makes it so that our inverse is a function. Don't worry about it till the end, though. So if you go ahead and swap x and y, and then solve for y, we're going to have to divide both sides by 4, and then take the fourth root. Now, if you're taking the fourth root, don't forget even roots, you're going to need a plus or minus. And then fourth root of the whole thing, or you could do top and bottom separately. Typically, I'd have you rationalize since it's a fourth root in the denominator, but thinking about it, I think we're just gonna leave it. You'd have to multiply by 2 more factors of 2 to get 4 of them total. I'm just gonna say we can leave it with the radical in the denominator this time. Now, where that inequality comes into play is if you were to graph this, look at it, think about it, it's not a function. So the inequality tells us that we want to make it a function by using only 1/2 of it, the part where your x values are less than or equal to 0. So we're going to only use the negative part. And if you're good with that, you can ignore this last part. But if you're like, wait, it says x is less than or equal to 0, and I just changed the sign on the whole thing, well, that's because in our original function, we took and swapped x and y. So technically, this is saying that the y's on our new function are less than or equal to 0, which we have by changing the sign and having the negative out in front. Okay, so we've got this function that gives us the cost of producing n items. So our original is if we plug in the number of items we're producing, it outputs the cost. We want to find the inverse of this model. So the inverse is going to swap the input and the output. Instead of plugging in the items and getting out the cost, we're going to plug in the cost and get out the number of items that it would have taken to have that production cost. So to start with, I'm just going to write this as y equals 360 plus 0.6 times my number of items. I'll go ahead and just swap my n and my y and then solve for y. The letters that these things represent are not going to necessarily match our original representations when we find our inverse, but go ahead and swap them. So if I am solving for y, I'd subtract 360. I like fractions, so I change that 0.6 to 3/5. So dividing by 3/5 on both sides means I'm going to multiply both sides by 5/3. And if I go ahead and rewrite it with my 5/3 being multiplied that, I'm going to put some parentheses around it to remind myself I need to do it to the whole expression. I'm going to multiply and end up with 5n minus 1800 all over 3 equals y. Okay, and since my input and my output have swapped, the letters don't really make sense anymore, so I'm going to change that to n to a c, because remember, I'm plugging in my cost, and then I'm getting out the number of items, so I'm going to call this function n of c, number of items that get out when I plug in my cost. Okay, Now I'm going to find the amount of items produced if my cost was $615. So I can use my inverse function, plug in 615 for C, my cost, and then get out the number of items that it costs that much to make. So if you do that, you end up with 425 items. So this would be useful to have an inverse if we were going to do this calculation multiple times over and over again for different production costs. We're going to talk about how you can verify two functions are inverses. So say you have two functions and you want to know, will this one undo that one? Well, if you do function composition, the first function followed by the second one, and you get back to your original, and you turn it around, do the second one followed by the first one, and you get back to your original value, then those two functions undo each other and are inverses. So I can verify, or essentially kind of show/prove, that two functions are inverses by performing function composition on them and seeing if I get my original input value, which in these functions is x, back. So let's see if these two are inverses by first doing f of g of x. So I'm going to take my function g and plug it into function f and place in my variable. So if you actually do that, you get x minus 2. Oops, I realized I forgot the plus 2 on my f of x. So yeah, you end up with your original input variable back when you plugged g into f. We need to turn it around and try it the other way. So if I take f of x and plug it into g of x, I want to see if that gets me my original input value back. So I'll take 4x plus 2, replace x with it in g of x, and then if I multiply that 1/4 in and simplify, I do get back to x. So both times we got our original input variable back. That means they are inverses. If you do not get x back, they are not inverses.